Those. Those are awesome. All right, let me give us a few moments for everyone to take some time to answer this. We got scream at laugh or out of air laugh. We have giggling, the silent laugh. So giggling can have its charms. Like when I was in high school and something was funny, but you weren't supposed to laugh because the teacher was there, it just made it more funny though. Like you just want to keep giggling. So the giggling has its charms for sure. Especially like you're trying to not laugh and it makes it more funny. All right, we got more silent laugh. Definitely. It's been a while since I've done those. Something has to be really funny for that laugh to happen. Ooh, one that's missing, everyone. The crying, laughing and crying. Is that on there? That one's good too. I'm gonna put laughing plus crying on there for today. I love those. All right, let me go ahead and have a check-in on who we have here. Again, based on the check-in question here. If you still haven't answered it, feel free to. You could also do it privately, like some of you have. I think we do have a few missing, so it'd be great to round our friends up to come on into math class. We do have some credit today. Class credit. Let's get that credit. Oh, we're getting more folks coming in. All right, so this is who I'm missing right now. I'm missing Shema, Kalia, Justin, Jayla, Jayla, Ernesto. Am I missing Shaylin? I'm sorry if I missed you. Let's see. Yeah, I'm also missing Shaylin. Missing Jose, Jonathan, Jaleel, Amara, and Zakaya. So that's who I'm missing. If you're actually here, please let us know. For those that just came in, we had a little check-in right here. And what's your favorite kind of laughter? Let me do this once more. So I'm missing Shema, Kalia, Justin, Diva, Jayla, Ernesto, Shaylin, Jose, Jonathan, Jaleel, Amara, and Sakaya. So let's get our friends in. And we have another vote for giggling here in the private chat. Definitely. Yeah, so this is fun. This also made me think of stuff I find really funny. So yes, hopefully y'all get to laugh some today or sometime soon to get some laughter in your lives. We all need that. Thank you so much for answering that check-in question, everyone. Let me go ahead and transition us into the agenda here today. We just took attendance with a check-in question. I'm going to do a recap. And today's credit is actually going to be a Padlet, one question on the Padlet, and a Google form. Today's credits, everyone. So just be mindful to make sure you complete that. I enter them right after class so that I don't lose any. The third thing on our agenda is if we have time, we'll talk about cosine. If we don't have time, no big deal. We'll have a checkout question and then asynchronous number 12, everyone. So we're nearing the end of our module and it's a little bit funky because next week is spring break, but right after spring break, you still have this module for 2 days. So we're still going to continue on the mini final coming back from spring break, even though it's going to be weird. So I acknowledge that. It's definitely going to be weird coming back from break and jumping back in. So, but anyways, aside from that, asynchronous number 12 has been posted. This actually has 2 parts to it, and it is actually the mini final. So you could actually take a look at the mini final now. Asynchronous number 12 is basically you doing part 1 of the mini final. There's 2 parts to them. And this first draft of part 1 is due Wednesday. So again, no pressure. This is a draft. It means it has imperfections and mistakes on it, and that's fine. Let me know, does anyone have any questions about our agenda, about what's coming up for us? Let us know. Let me just pause here. All right, I don't see any questions. I was also replying to see if someone had some difficulty getting into the Zoom, but it should be the same link. Yeah. But okay, let's go on, everyone. Let's jump into the recap. Oh, okay. Actually, there's a question before we jump into that. Thank you so much for asking. How much of our grade will the mini final be? Usually, let me think about this. Usually it's about 30%, about 30 to 35%. So it could, for example, if you have an A and you don't do it, it could drop your grade to a B. So I think it's like a whole letter grade if you think about it like that. That's how much of the grade the mini final will be. That's a very good question. Are there any other questions on that? All right, awesome. Let's go ahead and jump into the recap. Recap. Okay, last week, because it's been a while. It's like we always have, I always see you on Tuesdays. It's weird. I don't see you on Mondays. But we had this essential question that y'all went into. Remember that we all had little mini groups and you all tried to figure out how in the world is a unit circle connected to a wave, like a sine function wave, like you see here in this picture. We're trying to investigate how this connection is even possible or how we can use the unit circle to create this model. I am on slide number 4 on our slides, by the way. Again, our slides are on Google Classroom. We are on day 7. And not only that, but we talked about how exactly does a circle give us a wave. And how it happens is if you read up here, a sine wave is formed if you imagine that there's a point on your circumference of your circle and you're basically tracing its height over time. And I specifically put vertical height over time, or I put over some input. Sometimes your input isn't time, but it does help us understand if we think of the input as time. The best example that we talked about last week was imagining you boarding a Ferris wheel. And I specifically mentioned that this reminds me of a Ferris wheel that used to be set up in Southland Mall. I live in Hayward, so they would always be like these a fair that would be set up like probably 3 times a year or something. And I'd always be excited to go on the Ferris wheel. And you would board it right at the bottom. Sometimes you board Ferris wheels like in the middle. Some of them you board at the top. It depends on what Ferris wheel, right? So at Southland, I had to board at the bottom. So rider boards here. And then over time, you go up and up and you get to enjoy a nice scene. You're the rider. And what we want to measure, you see this popping up right here, is basically your height over time. Like imagining I'm the rider, I'm a point moving on the circumference of this Ferris circle, and I want to trace my height over time. When I do that, that becomes a sine wave like this. So this is what we looked at last week. And let me just bring back my little annotation tool just so I could point out. So this is when I board the Ferris wheel. I'm at a height of 0 feet, or actually this is 0 meters in meters. So I guess we're at 0 meters. Then I'm going up, up, up on the Ferris wheel. So my height is increasing, as you can see here. It is increasing, increasing until I probably hit the very highest height right here. That is the highest height, and that is this peak. Afterward, you go down on the Ferris wheel, so your height is reducing. And that's why this wave starts to decrease. Your height starts to decrease until you reach your initial position again, which is back down to 0 meters right here. So that kind of, this wave represents one rotation on the Ferris wheel. And it looks like it took about 3 minutes for me to complete this one rotation. But of course, usually Ferris wheels, you keep going around and around. So let me use another color to kind of show you this. So it looks like I went around once right here. I went around twice over here. And then 3 times. And then perhaps it stopped here and then we got stuck in the middle or something, or stuck at the very top. So that is how we use a circle to create a wave. Imagine that you're on a Ferris wheel and you're graphing your height over time. That is how this Ferris wheel kind of connects to sine waves. And that's how, in general, the unit circle will help us make sine waves or any kind of waves. Does anyone have any questions about this one here? Let's see, there's something in the chat. No problem. Thank you all for those who just came in. I appreciate you. Let me make sure I update the attendance. Yes, I got your message for those who just messaged me that you came on in. But if you didn't message me, you want to make sure you do so I can mark you present. All right, cool. I'm going to clear up my screen unless anyone has any burning questions about how to connect Ferris wheel to wave. Okay, cool. And if questions pop up later, of course, feel free to ask. I am always happy to take time to discuss this with everyone. All right, on our slides, I'm moving on to slide number 6. So we didn't really get to discuss this last week, Thursday, when we ended class. We didn't get to synthesize this big idea. So we're going to go ahead and do this now. So waves, right? Functions a model wave-like behavior like the one we just seen. The height in the Ferris wheel is modeled by a wave. These are actually called sinusoidal functions. It's a weird name. Sinusoidal functions can either be sine or cosine functions. So as you can see here in blue, this is cosine, and then yellow, this is sine. The only difference between them, it just looks like cosine is kind of shifted to the left by like pi over 2 units. So this is pi over 2. So it looks like cosine got shifted about pi over 2 units this way, and sine starts here, as in like its highest point starts there, its highest point for cosine starts over here. So it got shifted that way for cosine. Another thing I want to point out is take a look at the inputs. So sometimes the inputs can be radian measure or it could be degree measure. But I'll go ahead and tell you right now, in mostly upper level mathematics, they prefer to have the radian measure as an input. Equations and things like that are just easier when we have radians. But you'll see that in upper level mathematics once you hit there. But just to have a little note, because prior to this, right, I just showed you the Ferris wheel. And for the Ferris wheel, the input was time. So sometimes you don't have radians or degrees as the input. Sometimes it could be time. So just pay attention to the inputs whenever you're given a wave. Like, what are we measuring over time, over radian, over degrees? Like, what is it? Okay, next line of business. Let's talk about what is a periodic function. So that is actually a term we should definitely know. It's going to help us as well in our mini final. Periodic functions are basically the functions that repeat over time. They repeat at regular intervals, and one period is basically a length of one of those intervals. So if I'm looking at this graph here on my left, this looks like a sine wave. And if I'm imagining that I'm on a Ferris wheel, I think it started at 0. I went up to the maximum of the Ferris wheel. I go down to its minimum. Then I go back up to my starting position. So imagine that this is like a continuing wave. So this wave is repeating forever. So you could keep extending this. And how you could extend it is just imagine that you're riding the Ferris wheel forever. That would be pretty horrible. So periodic functions are functions that create a repetition of values. This one right here doesn't really look like our sine function because it looks very boxy. It kind of looks like the top of a ghost head or something, but this is also periodic because it repeats. This shape right here keeps repeating. So this is also a periodic function. That's how you can visually kind of identify them. And for the technical definition, you can look up here. This is your technical verbal description of what you see happening in these graphs. And then let me see if anyone has any questions about what we're talking about here. This is a definition for what is a periodic function. And waves are periodic because they repeat. Because you could keep going round and round on the Ferris wheel. Or sometimes sound repeats, and sound is a wave as well. Welcome, welcome. Those just coming in. I'm so glad y'all are here. You want to open up today's slides? Today is day 7, and we were on slide 7 discussing what is a periodic function. We're going to soon have a Google form to check our understanding of this. So definitely follow along. We also have one Padlet question today. Let me just mark us here. All right, I'm so glad y'all are here. All right, let me clear my screen. Okay, so that was a definition of periodic function. Oh, okay. Sorry, y'all. I have a question here. How do you explain the intervals for this function? Like when it says up here, it creates a repetition of values at regular intervals. I love that question. It's a very good question. So interval means on the x-axis, we're talking about like the domain. So for example, let me just pretend like I'm cutting up this part that keeps repeating. I'm just gonna slice it here. I'm just gonna be like, okay, I have identified that this part of my graph keeps repeating over and over. So I know it's periodic first off, but what is like over which interval is this repeating on? Interval means basically the length of your domain. So after every length of this, so basically for this one, the length of this is basically, it looks like it's 2 pi. The length of this is 2 pi. It's in radians. So what that means is for every 2 pi, this function is going to repeat the same shape. So that's what I mean by interval. So it's basically the domain. So every blank is going to repeat the function. So that is what our interval means here. Let me just make sure I write it down. So for this example, so every 2 pi, my function's output values, which is your y values, output values will repeat. And then regular intervals are the x values or length of the domain, which is your x. So that is what I mean at every interval. So for this example, at every 2 pi, you're going to get that repetition. And regular means every 2 pi. And it depends. So some functions have different interval lengths. That was a good question. Yeah, thank you. It's also, by the way, like I said, I sometimes I learn from you all when it comes to verbalizing things. And so that was a helpful question because it's pushing my thinking as well. Because I'm like, yeah, what do I mean by interval? So that was a very good question. Let's see if there's any others. So I'll just pause here. All right, awesome. I'm going to go ahead and clear my screen. And let's go on to the next slide, slide 8. So now, okay, good. We kind of know a visual example of what periodic functions mean. Now, let me also give you the formal definition of it. So when a function is periodic, it has a period. So when a function is periodic, it has something called a period, which we call P. And when it's periodic, it has this property. It has f of x plus p equals f of x. Basically, it's kind of like what we saw prior, where your period is the length of that interval that is repeating over time. So basically, x plus whatever, like after certain 2 pi or whatever, you're going to get the same y values. Or you could take a look at this example right here. And this is for all values of x and x plus p in our function's domain. Domain means your x values are basically your inputs. So this is the parent function for sine. Sine starts at 0, goes up, crosses down back to 0 at pi, goes down to -1, and then comes back up at 2 pi. So one length of a sine period is going to be 2 pi. That is one length right here. This is a portion of the graph that repeats forever in all directions. So my p here, the length of this is 2 pi as well, just like that other one had 2 pi. So how would I use this definition up here? We would basically say this. So this function is periodic because it fits the definition, because in this particular example, the p, or my period length, is 2 pi. After every 2 pi, this function is repeating, is what this means right here. So after every 2 pi, we're getting the same output value. So let me just pause here to see if anyone has questions on this one. So this is kind of like your technical definition. So prior to this slide, we kind of had a more general definition, like, oh, if you could look at a graph, can you tell me if it's periodic? This right here is more like the technical algebraic explanation for a periodic function. And again, periodic functions have something called a period length because they repeat every time. And that's the length of their period, how often they repeat. And then let me pause here to see if anyone has questions. But this is for this particular example. Let me also make sure I draw an arrow. Because the length of one cycle is 2 pi, you just replace this p right here with 2 pi. So this is for that particular example. All right, awesome. I'm going to go ahead and clear the screen up so we could go ahead and jump into some application. So I'm bringing back this Ferris wheel with the same graph that we talked about and looked at. So this is like us looking at this a third time. But one skill that you definitely want to get from this is finding the period of a periodic function. Again, you could go back to our prior slides. We have defined what the period is, and we're going to go ahead and apply it here. So here we go. So we have the same old Ferris wheel. We have its wave that's graphed. Cool. Let us find the period. So we're going to have to identify, okay, where does this start? Where does this end? Where I kind of already talked about this. So remember, y'all, when I boarded the Ferris wheel, I started at a height of 0. I had to go up on the Ferris wheel until I reached the very top of the Ferris wheel. Then my height was decreasing over time. And then I went back down to my starting position after 3 minutes. So for this particular example, one cycle or one period is 3 minutes. So one way to find the period of a graphed function is to just figure out, where does it start, where does it end? Cool, that is the length of one period. So let me go ahead and put that here. So the period for this is 3 minutes. That's how long it took for me to get on the Ferris wheel, go around it once, and get back to my starting position. The rest of this is, it's going to repeat, right? The cycle of me going up and back down, that cycle repeats every 3 minutes. That's what period means. But guess what? This is not the only way to figure out how to measure a period of a function. So I think right after this, we're going to have a Padlet check. So definitely pay attention on how we're finding the period of a graphed function. Okay, so this is one way. Figuring out where your wave starts, and where it ends. That's one way, right? We figured out 3 minutes. Cool. Color that in red. Oh, okay, whatever. Okay, there's another way. And the other way is actually the way that I'm going to be using. So I'm going to go ahead and clear the work here to show you that other way. So let me clear this. Unless anyone has some questions, I could undo that clearing. Okay, the other way is going, oh no, I undid the words here. There we go. Let me just use the eraser. Oh, there's something in the chat. Will you be posting this recording on Google Classroom? I've been posting my recordings on Remind, but I could also post them on Google Classroom if that's helpful too. I could do both if that helps everyone. Let me know what y'all prefer, but I sent yesterday's recording. No, that was for period 1. So I could send today's recording. I also do it by request as well, but I could post it on Google Classroom if that helps. I could post all of them actually from this module. I've been recording all of them. So yes, for sure. Okay, so that was one way. So let me show you the way that we're gonna be doing. It's like faster for me. So another way, and the words are right on top of it. So sorry, I gotta delete that, unfortunately. Sorry. The other way is strategy. Count the distance between two maxima. Maxima, what does that mean? Maxima basically means, give me a sec. Maxima basically means like between two peaks. So let me write that down. So maxima means like two peaks or two high points. Between two peaks. So what do I mean by that? Let me show you. So let's say I didn't know, like I don't know where I'm boarding the Ferris wheel and I don't know where this cycle starts. So I don't know the length of the period. These waves all look the same to me. So I don't know. Okay, here's the strategy. You're just gonna count the distance between two peaks or two maxima. So I identified here's a peak. Here's another peak. I'm going to draw a line to connect those two peaks. And basically why I'm drawing a line is because I want to figure out what is the distance of this line or what is the length of my line. Well, I don't know. Like unless I have a ruler, how am I going to figure this out? There is a strategy you can do. Okay, I drew my line to measure the length between these two peaks. Well, we can use our x-axis, see down here? We can use our x-axis as a ruler to figure out what the length of this period would be. So you're gonna see right now, this is gonna visually get copied and dropped down here. I'm gonna use the x-axis as a ruler. See that? So I took this length and you see this red line, it appeared down here. And then lo and behold, you get the same thing. The fact that one cycle or one period length is 3 minutes. So you get the same answer, but this is the strategy that we're going to be using. It is kind of the most helpful strategy to figure out the period or the length of a cycle of a wave. So let's see, does anyone have questions about this strategy? How we're finding or measuring the period of a wave? Again, you're measuring the distance between two peaks or two maxima. You're using the x-axis kind of like a ruler, and then you kind of see where does that length end up at, and here it ended up at 3 minutes. So that is the strategy that I'm doing, and that is how we get the answer. Once again, that the length for this particular function for one period is 3 minutes. 3 minutes down here. Let me circle that. So one period for the period is 3 minutes once again. Okay, so I think right after this, we have a Padlet check to check our understanding on how we are finding the period of a wave. And I did this in particular with the Ferris wheel example. Does anyone have any questions before we jump into that Padlet? Okay, awesome. Let me clear up my screen and let's go ahead and check this out. Padlet. All right, y'all. I just went over how to find the period of a wave-like function. Formal word, of course, sinusoidal. But what I did is I just found the period of a wave and I discussed my strategy. If you forgot the strategy, it's on slide 9. It's right here. And we are period 3. So we're going to be going on the Padlet. Again, this is 50% of today's credit. And then we got a Google form. happening after this. So let's get on this Padlet. I'll open it with you. And we're gonna just check our understanding right now. Yay, I see someone there on the slides, awesome. So if you're on the slides with me, you just go to slide 10 and click on period 3's Padlet. All right, let's see. And I'm gonna direct us into which column we're gonna be writing on today. All right, and we are on, now why does this say Desmos animation? Let me junk that. Okay, we are on column number 9. So in your own words, I want you to explain your understanding on how to find the period of a sinusoidal function. Sinusoidal function are basically a wave function. Again, you can reference slide number 9 in today's slide to kind of help support you. If you're stuck and you have questions, go ahead and put your questions down. Put your name or initial for your credit here today. We are on column number 9. I'm going to go ahead and give you all about a minute or a minute or two, and then we'll check in. Please make sure you put your name or initial for today's credit. Hello, everyone. I can see many of us are still putting down our thoughts. So I'm going to be giving an additional 1 more minute on column number 9. Let's get today's credit, everyone. Let's be back in 1 minute. Hey everybody, we are coming back. I am seeing some interesting stuff coming up actually, so I went ahead and highlighted the three different trends that I'm seeing. I do see a fourth trend actually, so I'm gonna highlight this one. Oh, no, 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 I'm not trying to cancel. Okay, sorry. Let me, so I did different colors. It kind of looks like Easter eggs. Easter's coming up. Okay, sorry. So some of us used like that formal definition that I showed you all. I believe it was on slide number, no, slide number 8. So today I showed you that formal definition for using a period, which is awesome. Another thing I saw was to find the period of a sinusoidal function is dividing by the absolute value by 2 pi. So I'm thinking about like, oh wow, where did we see this? Actually, that's coming up in our next lesson. So I wonder if y'all are bringing in some prior knowledge. So this is very interesting. This is the method that I showed you all right now. So this was on slide number 9. You can find the period of a sinusoidal functions by you counting the distance between two maximums, and that's going to give you your period. um we have this is, and I'm wondering like, oh, are you guys coming in with, ooh, are you guys coming in with background knowledge? This we're going to talk about in our next class period. We're going to talk about this is like kind of a way to transform wave functions, so that's interesting. But if you have this, how do you find the period? And I believe I saw Jasmine had a little bit of a formula, so that was interesting, definitely. Whatever is your understanding on how to find the period, make sure it's one that you understand. Definitely. So if you're given a graph, you can tell me like, oh, the period is this. And again, these are the different ways everyone else is understanding how to find the period. Wow, thank you so much. And again, if I didn't highlight your answer, just because it was repeated, so I just clicked on the repeating trends I was seeing, which were these 4 different repeating trends. So awesome, y'all. I'm going to go ahead and take us back into our slides. We're now going to go ahead and try to find the periods of some functions. So I'm going to take us to slide number 11. So for those of you who brought a different perspective on how to find the period of a function, see if you're able to apply it here in this example that we're going to be looking at. So I'm on slide number 11. Finding the period of this. And then after these 2 examples, by the way, everyone, we have Google Form, and that's going to be part 2 of your credit. So making sure you did the palette and then you do your Google Form. So let's do this. Okay. Let's find the period of the following. So I'm gonna stick to my strategy, but again, you feel free to bring in any other strategy that you are comfortable with. So the strategy is um, finding the distance between any 2 maximums. You could even do minimums if you desire, but let's just focus on maximums. Now, there are various different maximums I see in my graph. By maximums, I mean highest points. I see one here. I see one here. There's a lot. So I could choose any of these 2 as long as they're next to each other. And I believe I chose these 2 just because, I don't know, they're positive. They're in the positive x-axis, so I just like these. Okay, so this is the next step. I need to measure the distance between these 2 maxima. So let's just imagine that I'm measuring this with a pencil or something, or with your fingers. Like you could just do that. Okay, the next thing I need to do is I do not know what the length of this red line is. How do I know that? Your next step is you want to use your x-axis. Let me circle that. Use your x-axis as a ruler. Just imagine that this is your ruler. So let's say you have your fingers spread apart. You just go down, like keep it like the same length and just go down to the x-axis and see what that length is. So I'm just going to imagine that I did that with my fingers by just moving that length down. See that? I simply kind of just copy and pasted the link down here. Again, if you're using your fingers, same thing. You just take that distance and move it down to the x-axis and check out your length. So according to this function, this one here, the length of one period is going to be 4 pi. So this function's wave is repeating every 4 pi units. So each time 4 pi happens, it's going to repeat its wave. So the period of this is 4 pi. See if I wrote anything down, but Let me write down the answer then. So the period 4 pi. That's our answer. We were only asked to find the period, so it looks like we're done. Does anyone have questions about this example? Okay, cool, cool. I'm hoping that's good. All right, let's do one more example, then we'll jump into our Google form. It's gonna be the last thing, our Google form. Okay, next example, another wave right here. Let's find the period of this wave. So this wave looks kind of more scrunched together, but the strategy is gonna be the same. I notice there's a bunch of maxima, right? As long as you choose the maxima and they're right next to each other, I'm going to be choosing these two right here. And I'm going to again do that strategy where I kind of just measure. You can measure with your finger. Um, yeah, measure with your finger or so. So I'm noticing that I went a little bit over, just so you know, y'all. So I feel like I made my line a little bit over. And like with your finger, you would just take that distance and just go to your x-axis. You're using your x-axis as a ruler. So I'm going to take this and kind of just plop it up here to see what that length is. And see, it went a little bit past, but that was my fault. I went a little bit past the maximum. But this period for this particular function is going to be 2 pi, because that's where that ended up at. And again, your x-axis was used as a ruler. So our period is going to be 2 pi. 2 pi. Okay, so that was my last example before we're going to hit into the Google form. Are there any questions though, like burning questions or anything before you hit that form? The Google form, by the way, y'all, is not great on accuracy. So you're not supposed to stress. It's more so a process check for you. It's also information for me to know where everyone's at in their understanding. So as long as you do it and you give your best thoughts, you will get an A. So you just do it, you get an A. So just give it your best thoughts. Um, but yeah, so let me know if anyone has questions about this last example before I move us into that Google form. If you're on the slides, you're already can go to slide 13 and open up the Google form. All right, awesome. Let's get to it then. Okay, y'all, this is the process check Google form. Again, this is supposed to be not something that you are afraid of. This is more so something that you're just checking, like, where is my understanding right now? I'm gonna go ahead and put this into the chat and I'll start our timer. We're gonna be coming back right at the end of basically class. So again, this is second part of our credit today. And I put little visuals about where certain people are at. I do wanna normalize that some of you are like, I got this. And then some of you perhaps are stuck. That's fine and that's normal. That's why you wanna do this form so we could see where you're at. I could see where you're at and you could also do a mental check of where you're at. All right, everyone. So please let us complete this form. Let me go ahead and start the timer. I'm gonna turn off my video and my mic so that y'all can focus, but I'm here for any additional like questions. Just send me a direct chat and then we'll come back at the end. All right, everyone, we'll have about, and it looks like about 9-ish minutes. I'll just put the timer right here.